You can hear me?
This call is now being recorded.
Okay. So, I hope mnanisikia. So today we're going to do negative feedback in amplifiers. Let me just get my notes here. Okay. So today we're doing the topic feedback in amplifiers. I'll try to take as little time as possible. So I've compiled some questions. I hope you've seen them in the group. So let me start with a quick summary. So, okay. So if you come under, okay, if I'll break at some point, just let me know. So the first thing I need you to remember or to know in this topic is we have our normal amplifiers. Yeah. A normal amplifier looks like this. So we normally have voltage in, and then we have amplifier gain, and then voltage out. So this voltage out, it is amplified by a certain factor. So this is how a normal amplifier looks like. But an amplifier with feedback, it means some fraction of the output is sampled. So some fraction of this output will be sampled and like put back, okay, and return back to the input. So it's like we'll have two inputs. We'll have this actual input and we'll have the input that is returned. So let me show you guys that. Okay, first, mnanisikia? Someone just say yes so that I know.
We can hear you.
Okay, so now this is an amplifier with feedback. We have our V in, our initial input coming in, and then it is amplified by some factor, AV, or gain AV, and it produces V out. Now in feedback we've said some fraction of this V out will be fed back or returned into the input. So note that the fraction of V out that is fed back is this one. So it is the feedback factor, K, times the V out that is fed in. So in our input side, we'll be having V in, this one, plus the input that is fed back, the output voltage that is fed back to the input. Hope naelewa diapo. So this is one important expression. I think that is pretty straightforward. And then V out, of course, normally we know amplified voltage is voltage gain times input voltage. We end up upper. So you have equation 1 and 2. And because we know V in, this V in is this one, we'll substitute it. So I came and said V naught or V out is V times V in, which is VI, plus K V out. Hey, so from there, I think from there it's easy because you're only now going to do V out. Make V out the subject rather. So yeah, multiplied AV times VI, AV times KVO, V out to get that. And then I factored out V out. Okay, first I brought this expression on this side so that I end up with this. And then I factored out V out in this expression. So the method is in J. So I end up with 1 minus AV or voltage gain times K. So K is feedback factor, don't forget about that. So we have V out is AV, VI over 1 minus that. Now, we know gain is voltage out over voltage in. So if I divide voltage out over voltage in here, so over V1 here, let me use a pencil. So over VI here and over VI here, this will cancel. So I'll end up with V out over V in is voltage gain without feedback into 1 minus K AV. So every time you see an expression written with subscript F, inamaanisha kuna feedback. So this is gain with feedback. But this other one is gain without feedback. So make sure you're very keen on that. And you realize that when there is feedback, gain is reduced. So you're seeing it's like your normal, your gain without feedback is reduced by this factor. So this is, I've highlighted that because it will help us in understanding bandwidth and noise and distortion. Okay. So anybody has any questions up to there, or ama niendelee? Okay. Thank you guys. Okay. So what does the prime thingy indicate? I just think it is to differentiate between, it's to show you that there is some voltage in the output that will be fed back in the input. So yeah, basically that's what I think. Okay. So positive feedback. So these are like cheat points or hints. So positive feedback, we say that the product of voltage gain and the feedback factor is positive. A negative feedback, the product of the feedback factor and the voltage gain is negative. So, okay, the most questions I've seen rather are on negative. So this is something you'll have to remember, and you'll see how we'll apply it later. Another thing I'd like you to remember is we've said gain reduces by a factor. Okay, so from this equation, we've realized that feedback gain, it will reduce the gain without feedback by this factor. So when you come here and you're being told that this was like one of the reasons for negative feedback. So one of them is that there's decreased distortion. And we're being told distortion is directly proportional to gain. And you know gain is being reduced. So if gain is being reduced, pia distortion itakuwa reduced because it's proportional to gain. So distortion with feedback will be distortion without feedback divided by this particular equation. Same thing applies to noise. Noise is also directly proportional to gain. And because we said gain is being reduced by a factor of 1 minus KAV, then noise without feedback will mean it is noise with feedback divided by 1 minus KAV. So yeah, that is a relation that would help you understand it very quickly. Another thing I've seen they were asking is about input resistance. So input resistance in our notes, we were being told that output signal fed back in series will increase the input. So we'll do a question where we feed back the output signal in series and you'll see what's going on. And then for output resistance, so for output resistance, we're being told if that output resistance is R0. So this is output resistance with feedback.
Selecting.
Yeah.
Before you go any further, I have a question. Or like, could you explain how the whole thing for input resistance? How when it's in series it behaves in such a way, in parallel it behaves in such a way.
Oh, okay, yeah. So for input resistance, we're being told if the output voltage or current is fed back in series with the input, then the input current decreases and effective resistance increases according to the following relation. So if we feed back the voltage in series with the input, then it means input current will decrease and effective input resistance will increase according to this relationship. I can't say I really researched exactly on the nitty-gritty on this because I just used the formula in a question. I don't think I really had time to go deep into the information. And the only other thing you have to know is if output signal is fed back into input in parallel, the input resistance decreases by an amount depending on the circuit. So if the signal is fed back in parallel, then R will decrease, not increase. Yeah. So we'll do questions so that you understand what's going on. And then for output resistance, we were saying that if output voltage is returned to the input, either in series or in parallel, the output resistance decreases. So if I return output voltage in series or in parallel, my output resistance with feedback will still reduce by this factor. So we are going to do questions so that you understand what's going on. Okay. Yeah, so I think we can start doing questions and feedback. So here, I sent it to the group. An amplifier with 1 kilo ohm input resistance. So input resistance is Ri. So this is input resistance without feedback. And 50 kilo ohm output resistance has voltage gain of 40. Yeah, so this is voltage gain without feedback. The amplifier is modified to provide a 10% negative feedback in series with the input. Calculate voltage gain with feedback. So hapa tumeona we are providing negative feedback in series with the input. So let's see. Sorry. So first, let's calculate voltage gain. We've derived the expression for voltage gain. Tukapata that our gain with feedback is actually AV, gain without feedback, 1 minus K AV. Now, you remember when I said in negative feedback, this product, in negative feedback, it is negative. So this is something you have to remember. You have to remember it. So let's do this question. So of course we've been given gain without feedback, input resistance without feedback, and output resistance without feedback. Calculating gain, here we know our formula. So AV, which is 40 from here, 1 minus K. Now this negative is because we've been told in the question it is negative feedback. And because in negative feedback, when tumesema hapa, the product is minus K AV. So that's why we're using this negative here. So yeah, you'll end up with 4. So minus minus is a plus, so 1 plus 4 is 5. So 40 divided by 5 is 8. Is it clear till there?
Yes.
Yes. Okay, cool. So the second part. Whether these things are easy. If you guys thought topic 1 was a walkover, this one at sijui, you'll be flying. Yeah. And then the second part, you're being asked about input resistance with feedback. So input resistance with feedback, RIF, is Ri into 1 minus KV. And because it's being fed back in series, it means input resistance will increase. That's why we are actually multiplying by the factor and not dividing. If it was being fed back in parallel, then tungekuwa tuna divide. But now it's in series, we write here series. So yeah. So we're being given input resistance without feedback, Ri, let me see, is 1 kilo ohm. So that's why I have my 1 here. then 1 minus kV. Again, because it's negative feedback, yeah, we'll have 1 minus minus. Okay, was provide a 10% negative feedback, so 10 over 100 times AV 40. So don't forget this minus. Kama kuna negative feedback, it has to be minus up ili hapa ikuwe plus. Otherwise you'll be doing 1 minus 4, which is not correct. That would be positive feedback. So we'd have 5. And then we're being told to calculate the output resistance with feedback. So output resistance with feedback, we've seen this formula. So it is resistance without feedback, which we said was 50 ohms hapa. Then 1 minus, again, kV is, you use the same expression, negative hapo, juni negative feedback. 50 over 5 to get 10. So I hope this is a question I've seen almost in every year. It counts as 5 marks, if I'm not wrong. So I feel like this would be easy marks to get. So that's why I'm telling you it's a walkover. So I'm done with that question. I'm going to the next one. So here we're being told an amplifier with 10 kilo ohm input resistance. So this is a RIDE, input resistance without feedback, and 80 kilo ohm output resistance. So this is R out without feedback. Has a gain of 50, has a voltage gain of 50. The amplifier is modified to provide, so this is gain without feedback, AV. The amplifier is modified to provide 5% negative feedback. So by the percentage they give you is like your feedback factor. It's okay. Negative feedback. So again, for negative feedback, I've written this expression here in series with the input. So if the output is being fed in series with the input, it means that in resistance, tumesema resistance ita increase. So resistance with feedback will actually increase. So let's say first, let's find the gain. So gain with feedback is gain without feedback, 1 minus kV. So this is something you'll use a lot. And then we were told gain with feedback tuliona ni 50, ndio hiyo 1 minus. Again, there's a minus because it's negative feedback. So minus K is 5%, so 5 over 100 times AV is 50. For you to get your gain with feedback as 14.2. Resistance with feedback is resistance without feedback times this expression. So resistance without feedback we were given as 10. So we'll have 10 times 3.5. So 3.5 is the expression we got here. 1 minus or 1 plus 2.5 to get 35. Output resistance with feedback, okay, is going to be output resistance without feedback divided by this 1 minus kV. So yeah, output resistance was 80, we were given in the question, divided by 1 minus kV, so 1 minus 3.5. We divide the two expressions, we get this. Any questions so far? Any queries, concerns?
Wait, it's 80 divided by 1 minus 3.5.
I think, no, okay, no, yeah, no, it should be 3.5.
80 divided by 3.5.
Yeah.
Okay.
Okay, so you guys are okay?
Yes.
Okay, so these questions are really easy. Let me do the next one. So the next one, we're being told, I'll do this one with the noise, and then I'll let you guys do distortion. So I'll send the question on the group so that you can attempt it, because it will follow pretty much the same procedure as this one, the one I want to do right now. So So the application of 2% negative feedback to an amplifier reduces its total noise from 6% to 3%. Now remember, we said, now you have to remember your expression for noise. Noise with feedback is noise without feedback over 1 minus k. And we said this is because noise is directly proportional to gain. And because we are reducing gain, we're doing gain by 1 minus k AV, then because it's proportional to noise, we will also reduce noise. So this is where this expression comes from. So, yeah. So because this NF is being reduced, yeah, this is the reduced factor, then this is 3. So if you see in your question, the lesser noise will be 3%, and yeah, of course the other one will be 6%. I hope you guys understand that whole, why this is 3 and why this is 6, because we've said negative feedback, with negative feedback, the noise will be reduced by this factor. So, what was initial voltage gain? So what was initial voltage gain of amplifier when the noise was 6? So voltage gain is just that. So yeah, we'll pretty much substitute our values into this equation. We know this is 3, we know this is 6. We know K, okay, K was a negative feedback. Okay. So negative feedback, 2%, so you'll have 0.02 as K. So that is what I did here. So it came penye kuna NF. Okay, so I made okay, so let me just go through this pole pole. So I came and said that this is 3%, this is 6 here. So I made this the subject, nikaileta huku juu nikashukisha hii. So I have that N over NF, 6% over 3%. So I result, this is 2, so 1 minus KV. K, this is negative feedback. That's why I'm using negative 2 over 100 AV. So minus minus is plus, of course, so we'll end up here. If we make AV the subject, we'll end up with 1 over 0.02 to find the gain without feedback as 50%. Are you guys okay till there? Ili nisikwe naenda haraka, because this is just math. As long as you know this formula, una substitute to find AV. And then the next section asks, what was the gain with 3% noise? Yeah.
Hey, Mike asked a question.
Mike has to. Okay. Have negative feedback with an actual negative sign. If you have negative feedback with a positive sign, now remember we've said negative feedback, the product of the feedback factor and the gain should be negative. And for positive feedback, the product should be that. So if I'm doing my 1 minus KAV, this is negative feedback. But if I do 1 minus KAV, this is going to be positive feedback. Yes, it does make it a positive feedback. Okay, so Mike, I hope I've answered your question. Mike? Okay, so yeah, so let's do the next one. It says, what was the gain with 3% noise? So we said with 3% noise ni noise yenye near feedback. So if I'm calculating gain with 3% noise, it means it's gain with feedback. So yeah, and the formula for gain with feedback again, it's the normal gain or the gain without feedback, 1 minus kV. Yeah. So again, because it's negative feedback, there's a negative here. Okay, I didn't put it, but so we make a positive upper. We got AV as 50, 1, K is 2%, so 2 over 100 times 50. So yeah, your gain will be 25. If you have positive feedback, does the gain with feedback become negative? If I have positive feedback, so Mike is asking, if you have positive feedback, does the gain with feedback become negative? Does the gain with feedback become negative? Well, it will depend with the kind of values you'll have. It will depend with the values you have. Your values of this and this. But of course, if this expression is 1, then you'll end up with infinity. So yeah, but it depends with your value of this with this. There are no questions that the lecturer has tested on positive feedback that I've seen so far. So I don't want to like assume that you might not have negative. So yeah. So far I've not seen any with negative. Or at least the lecturer does not test much on positive feedback. Yeah. So yeah, we're done with the second Roman 2. So the gain with feedback ni 25. I hope mmelewa. Yeah, mmelewa.
Yes.
Okay, thank you. How much noise would there be if the gain with feedback was reduced to 10? So if gain with feedback is reduced to 10. So it's like our new gain with feedback is now 10. This is AV. Is now 10. We'll not use 6. You remember we were saying that and NF is 3%. We will use this as our original value. Actually, the reason why I wrote not in this equation is because it's like the original value. So our noise with feedback is 3%. So we want to find out how much noise will there be if gain with feedback was reduced to 10. So gain is 10, noise is 3%. So our formula for gain is gain with feedback, which is 10, is equals to the normal gain or gain without feedback into 1 minus, and because we're dealing with negative feedback again, we're using this negative. So 2 over 100 times gain. So if I make AV the subject, so this is purely math. This is purely math. If I make AV the subject, I'll end up with my voltage gain as 12.5. So this is my normal voltage gain. But I'm being asked how much noise would be there if the gain with feedback was reduced to 10. So we want to find noise that is, noise that is there when we reduce the gain by 10. When you reduce the gain with feedback to 10, it means that we have our gain without feedback is 12.5. So hapa ndio tutatumia hiyo 12.5. That's why we calculated it. Yeah. We've said our original value now will be 3%. Juu hapa ndio tumetokea from the last question. So we'll have 3% into 1 minus K, of course, is negative. So this expression will be 3% over 1 minus K minus 2 over 100 times 12.5. So this is what, if you calculate this, you'll get your answer. So that will be your gain with feedback. Okay. So there are no questions so far. So I'll move. I'm done with that question. So I'll send a question. So there's a similar question, but now wanatumia distortion instead of noise. So you'll actually, it's actually like the same question, because pure distortion, we said distortion with feedback is distortion without feedback over 1 minus that. So it's like you're using the same formula, only your n is distortion. So I'll send that question somewhere here. I don't remember. I'll move on to deriving expression for input feedback. I'll skim through it, yeah, but it's pretty straightforward. It's easier than even power amplifiers. So we want to see how we deal with these things in circuits. When I was doing negative feedback, I came about some types of negative feedback in a transistor circuit. There is current series, so there is current series, there is voltage series, there is current shunt and voltage shunt. But the lecturer only spoke about the two, and I've seen he's only tested the two. So I think that is what I'm going to go through right now. He mostly tests current series. So let me start with that. I did one question though, because I felt like after you understood the derivation in this question, it would be easy for you. So the question, this is not so clear. So there are some points that I want to give you here. So in current series, sometimes you'll have this capacitor, sometimes you will not have this capacitor. I don't know, this is what we call the bypass capacitor. So you realize when you have the capacitor and you do the AC equivalent circuit, this capacitor normally it shorts, yeah, it shorts out RE. So tunakuwa na wire hapo. So with this one, there is no negative feedback. So when there is no negative feedback, we find that our input resistance is just V in, which is VB. Yeah. So V in, which is VB over IBE. Okay, input IBE. Need to write this well. IBE. Is it IBE? Yeah. So normally, that is what happens when CE was connected. Your AC equivalent to mesema, it will short out this resistor. So we end up here. So this is something I want you to remember. And it is hii ndio tunaitwa H IE. We did it in first sem. So, and there's one more equation we'll remember from first sem, but it's not hard. So, and then, so we're being told all input voltage reaches the transistor. Now, without this capacitor, kama hii capacitor haiko, then we'll have RE here. So which means our V in will be VB plus the voltage drop here. So VB plus VE. And VE is IE RE. So with that, yeah. So we've seen V in is VB E plus IC RE. Yeah. This is IE rather, sorry, this is IE because it's on the emitter side. So to get input resistance with feedback, so the point I wanted you to know is that when the capacitor is not there, there is feedback. So in this expression, when the AC equivalent circuit looks like this, we know the capacitor is not there. So if it's not there, the input resistance you're going to be calculating is input resistance with feedback, because the moment there is no capacitor here, it means there is feedback. But in this case where the capacitor was there is no feedback, because now it will be shorted out. So that is a key point, because this question, we'll do a question rather. Sorry. So I hope umeelewa diapo. So input resistance with feedback is V in over IB. So V in yetu ni this plus this, hata tumeandika hapa, over IB, of course. So it's here. Na V in tulisema ni VBE plus IE RE. So IE RE. And you know IE from KCL is IC plus IB. So IC plus IB. So that's so clear. Yeah. So that is just what I've come and said here. Nimesema VBE over IB. This is this expression. And then IE ni IC plus IB. RE over IB. So this is where you'll end up. So remember again, this is still your RIF. Yeah. So if you remember in our derivation for the circuit that actually had the capacitor and had no feedback, yeah, we remember this one had no feedback. Chanaandika hapa no feedback. Na tumepata our Rin is VBE over IBE nani HIE. So because in this expression, yeah, so Rin tumeona ni VBE over IBE. So here in our expression tunapata VBE over IB. So if this is VBE over IB, then we know this is RI without feedback. So we don't put an F. So I hope you guys have understood till there. So that's why we replace this with this. Then we have, yeah, IC over IB. So this expression is basically IC over IB is beta. And you know beta is HFE. IB over IB is 1, yeah, RE. So do you guys have any queries or concerns up to here? Because this is what you'll be using to calculate your resistance, input resistance with feedback. So kuna mtu akielewa? Yeah.
I have a question. I've not understood why we are not saying beta is much greater than 1. Why we are not saying just ICRE.
Where we're not saying, sorry?
We are not saying it is. We would like it.
Come again?
I'm asking, when you're writing the VE, we said VE is IERE.
The VE.
Yeah.
IE.
So I've not understood why we are not saying, where we are not, you know how we keep assuming for beta much greater than 1.
We will actually do that later. So it will come in the end, like in the end of the, yeah. But for now, for here, yeah. Okay. So, but you'll see it, how it will come in later. So I hope you guys are good with that. Hope you are confused in any way. Okay. So if you check this analysis, damn, I get confused. If you check this analysis that we've done, it is so normally here we've ignored R1 and R2, bado tujaziweka. Yeah. So if I'm told to look for the input resistance, so there is feedback resistance and there is input resistance. So feedback resistance is what we call RIF. And input resistance is what the lecturer dubbed as RIF2. So input resistance seen by the signal, that is, this is the input resistance seen by the signal. So for me to find the input resistance seen by the signal, I have to come and include my R1 and R2. Yeah. So R1 and R2 is basically when you ground VCC. R1 inakuja chini ground na R2 iko hapo, so they're in parallel. So when I'm calculating input resistance, it's like the resistance I'm seeing from this side. So I'll have this one in parallel with A. So this is normally Ri. There's input resistance with feedback, and this is input resistance seen by the signal. So I hope that is, I wrote it cleanly here. So this is input resistance seen by the signal, and this is input resistance feedback, yeah, with feedback. So yeah, it will be R1, R2, we dub it as R, so RIF is parallel with R. So I hope that is okay. We can be told to find the expression for gain. So this is the one I was telling you guys will borrow from first sem. There's a place we derived it. I can't say I remember, but yeah, there's a place we derived it. But you have to remember this formula because you'll use it. So this is AI is current gain. So this is current gain, ndio tumeandika hapa as HFE. RL is just load resistance. RI, because you're using feedback, it will be our resistance with feedback. Okay. So, again, because it's negative feedback, we have this negative thing coming in here. I don't know whether that is the reason why you're having a negative in this particular one, or because we normally say current in our hybrid model. We normally say when tunasemanga current inakuja iwe chini. Please remember. But we'll do this with voltage series negative type, so don't worry about that. So yeah, remember to put this negative. So our input resistance with feedback, we have already derived this expression. And it's here. This is what we actually derived here. So input resistance with feedback is Ri 1 plus beta Re, ama HFE, current gain. So yeah. Okay. Ri plus 1. So we know this is input resistance with feedback, and because it's this expression, tutakuja to substitute hapa ndani. So if we substitute, tuko na negative HFE RL over this expression, because this is our input resistance with feedback. So Ri plus 1 beta times Re. I think that's pretty straightforward. So if you find a circuit with feedback, then this is the expression you're going to be using to calculate your gain with feedback. And then output expression, obtaining K. So obtaining your feedback factor, we'll use the two expressions for input resistance with feedback. So you remember when you are saying in series, input resistance will be increased when there is feedback. So we'll use that expression, and we'll also use the expression we just derived. So because they are both the same, this is this will equate. So if we equate the two, and then if you remember that Ri is HIE. So penye kuna Ri tutaweka HIE. Okay, I've just said that. So you have that. So it's just these two equations that I've equated. Now, our AV, it should be written in terms of the circuit elements. And that is where we are using hii expression yenye nimesema tulitoa kwa last sem. So that is where we are going to use this AV. So this we got it as negative HFE, RL, and that. So yeah, we'll come and substitute that here. So this one, this one we substitute it here. So that we have, yeah, that and that and that. So this is very mathematical, like hapa sasa ni tu arithmetic and algebra. So if we multiply HIE here, so this is input resistance times 1, tapata hivyo, then times this expression, it will cancel, tutabaki tu na hii ya juu. And then these two will cancel. If I take this on this side, it will be 1 minus the other, they will cancel. So I have this. And because again, we normally say HFE is beta, so beta greater than 1, hapa itakuja tuseme HFE RE. Yeah, this side is pretty much done. So to find K, you want to make K the subject of the formula. So you'll have RE over RL. I know the derivation is a bit, it's not hard, but you have to go through it again for you to remember. But when we use it in this question, you guys will understand. It will be so much easier. So find the figure below shows an amplifier with feedback, working with feedback. Working from first principles, determine the input resistance seen by the signal. Then we've been told input resistance. So HIE is normally input resistance. Is 5K, and this is because of what we did in first sem. And HFE is beta, of course, is 125. So this is our circuit. The first thing you note about this circuit is hakuna iyo CE hapa, hakuna iyo capacitor. So automatically we know there is no capacitor, so it means it has negative feedback. So that is how you would be looking at such circuits. Now when we ignore, so the first thing, we normally ignore this for, yeah, just a bit, so that we can be able to calculate our input resistance with feedback, that is. So first, of course, you'll draw the AC equivalent circuit. Okay, we'll ignore this for now. So we'll have RC itakuja kwa ground. So itakuja hapa, and it will be in parallel with RL. Then of course we'll have that, yeah. So I think that is pretty straightforward. So when I'm calculating my input resistance, I know I'll be doing input resistance at in with feedback, yeah, because we said it doesn't have a capacitor, so it has feedback. That's why I'm saying it's input resistance with feedback. Is going to be V in over IB. And our V in here is VB plus VE, and VE is IERE. So VBE, I have VBE plus IE RE over IB. So from here, you just have to squeeze kidogo hapa. I'll have VBE over IB. And then I'll also have IE. IE I know is IC plus IB. RE over IB. So this is what I'll have. as my input resistance with feedback. So when I come here, so this is what I've basically expressed till here. So again, we remember, without feedback, input resistance without feedback, tuliona kama ni VBE over AB. Again, it's because we had such an expression. Without feedback, we know the resistance, the capacitor is there. So we know we only have VBE here, and we have IB. So your input resistance without feedback is VBE over IB. And that is what we're saying, hapa ni Ri. Of course, IC over IB is beta, IB over IB is 1. So 1, beta is HFE, RE. Ri is HIE. So this is basically Ri. So we did it in the derivation, but now you guys get what's going on in the question. So we were given our value of input resistance. We tulipewa HIE hapa ni 5 kilo ohms. Current gain or beta is 125. So you have 5,001 plus 125 into 100. So you'll find your input resistance with feedback is 17.6 kilo ohms. Any questions still there?
Yes. The last thing.
Yeah.
If we go back to the diagram, the circuit diagram with feedback. Yeah. So, when you're doing the equivalent circuit, no.
Yes.
This
one?
Yeah. Yeah. So now do we ignore but do we ignore like the CC, the coupling capacitance?
No, but there's no coupling capacitance here.
No, here.
Where? Oh, this one.
Yes.
No, in AC, we normally say that we short circuit the capacitors. So itakuwa kama 2 wire.
Oh yeah, okay, sawa.
Yeah, because it's just AC equivalent circuit. Sorry, I didn't highlight that.
Okay, thanks.
So, okay, you're welcome. Any other question? Okay, cool. I hope mnaelewa. Nisikuwe nasonga na hamjaelewa. Because this is, it's like that topic when you unaingia exam and you just, this is easy marks unanyakua. Aya. So this is RIF. And you remember me telling you that there is resistance. I'm really writing badly. F2 and there is RIF. So this is hii yenye kona 2, RIF2 tulisema ni input resistance being seen by the signal. Okay? And we said when you're doing the one being seen by the signal, you have to include the resistors. So if I include my resistance, so the resistances I'm including ni hii na hii. So if I take this to ground, I'll have this in parallel with this. So I'll have 20 in parallel with 20 kilo ohms. So it's like this R is 10 because it's 400 divided by 20. No, 400 divided by 40, yeah, to get 10. So to get my input resistance seen by the signal, it is what I'm seeing here. I'm seeing this in parallel with the feedback RIF. This is RIF2. So what I'm seeing here is this in parallel with RIF. And that's why we came and did R1 in parallel with R2, and it's in parallel with RIF1. So tulipata kama 17, it's here. And then we just punch in from there. Okay. Yeah, I think that's straightforward. Voltage gain with feedback. This is, yeah. So this is also where this is now where I was telling you guys, still what I said. We're going to use the expression for last sem. Yenye tunasema gain is current gain, voltage gain is current gain times load resistance. Alright, now this one, this RL, should not confuse it. This RL is on the load side, so load iko hii side, so it is this one in parallel with this. So RL, capital RL, ni RE in parallel with this RC. Sorry, this is RC. Yeah. So I don't know whether this is RC or RL. Hata sielewi ni nini. So in parallel with. Okay, but you guys get it, yeah?
Yes.
Okay, Fiona, you have a question?
No.
Oh,
Obviously, you told you marks me that for all questions.
sorry?
Just continue. Endelea tu.
Okay, so yeah, this is current gain. Yeah, and there's that. So I put a note here. Do not use resistance seen by source. In this formula, you're going to use the resistance, the input resistance with feedback. So this is what we got. Do not use this one seen by source. Use the one by feedback. This is what applies in the formula. So beta is 125. We have that 17.6 to get that. Okay. So feedback factor. So this is just derivation, and I think we've done it. So because we've already done it, I'll leave it to you guys to also go and attempt it. Yeah. Okay. Now time is not on my side. I need to let Alvin present. So if you guys have any questions, you can ask. What I'll do, there is one question. Not this one. Yeah, so there's a question on distortion I was telling you guys about. Now here unaona tumeambiwa harmonic distortion is reduced from 8 to 2. So I'll send this one because it's same as the one for noise that we've done. And then the only other thing I want you to remember, one thing, is there was one here. I didn't do this question. I wanted to do it, but nilishona time. So I'll send this question too. This is interesting because it has a coupling it has a bypass capacitor here. So yapa, I don't think kutakuwa na yeah, I'm not sure because I've not done it. So there's that. There's one more thing I wanted to show you guys, but this is in our notes. There was a question on deriving. Let me see if I can find it real quick. Yeah, this one. This question says Figure 3D shows an amplifier with feedback. Draw the equivalent AC circuit of the amplifier. What type of amplifier feedback is applied? Like we've said, in the 4 types of feedback, in our notes, we have current series, voltage series, current shunted. Now we've only done current series and voltage series. So like the question I've done is for current series because you see even your format yake ama design yake inaka normally generally. But for voltage series, it looks like this. And we tuliandika kwa class. It's not in our printed notes. So it's actually, if you ask which type of feedback is applied, it's going to be this is supposed to be negative or positive? It's supposed supposed to be voltage. See, it is okay, whatever. But I'll send a photo of this one. It's in my notes. It's pretty straightforward. If you don't understand, I think you'll ask me questions so that I let Alvin present. So
Celeste, before you go, I have a question. If you go class notes page,
class
on page 44,
page
44,
page 44.
it's an example.
Okay.
In part 3 and 4 of the solutions. Is it part 3 and 4?
Then
Part,
what?
part 4, part 4, this part 3, this is part 4.
Part 4.
How he's done the solution for loop gain and the feedback in decibels.
I didn't see this. Loop
Why
gain.
did he evaluate loop gain like that? And why did he evaluate feedback like that? Okay, why did he define KV as loop gain when earlier in the notes we saw that AV with feedback equals AV over 1 minus KAV, right? That's what he called closed loop gain. Why is it that now loop gain has changed?
I'd have to look at this because I didn't look at it.
You wrote the must do. What happened?
Sorry?
Must do.
No, I did it when I was in school.
Gisheru,
Yeah.
I actually did the question. Wacha nitatuma solution kwa group ya hiyo example.
Nice.
Sasa. Okay, I will look at it.
Thank you.
Right, Sasa.
Alvin can present now.
Oh, alafu Celeste. Ngoja.
Okay.
Celeste.
Yeah.
Unakumbuka hiyo swali yenye kulikuwa na common emitter amplifier yenye umetuonyesha kwa past papers? Sorry, yenye iko na capacitor included, sorry.
Yenye kona?
Capacitor included kwa emitter.
The one
Yenye ulisema utafanya.
Nimesema tutaenda ku research hii hapa hivi unasema.
Actually kwa notes aliandika ka side, sasa sijui kama kuna mtu aliandika kwa notes zake page 43. So kupata feedback factor K normally ni capital RE over RL, sindio?
Yeah. Yes.
Haya, sasa kwa hiyo diagram, hebu rudi kidogo. R ya chini, capital E, the one with capital E. The feedback factor will just get using this RE, small RE.
So we'll ignore this one.
RL.
This one, sindio?
Yes.
Yeah. Actually, there will be feedback. Yeah.
Okay. Niache.
Thank you for that, Nigel. That is very helpful. Okay, Alvin, you can start presenting.
Okay, hi guys, can you hear me?
Yes.
Yes, someone please.
Yes.
So.
Yes.
Okay, so we don't have lights, so itabidi ni present from my phone. So let me present. Okay, can you see my screen now?
Yes.
Okay, so okay, so I've sent this document to the group. You can access it there. So Yeah. So I have some questions from past papers. Celeste alinitumia ndio nitatumia kupresent. So okay, the first question was here. It's saying the two conditions which are supposed to be met for oscillations to occur in an oscillator. So that's from the notes. Ziko hapo. There's the Barkhausen criterion, which is KAV must be greater than or equal to 1. And then the KAV must also be positive and real. Okay, and then kuna venye ana explain hapa how the oscillators don't have inputs. So over here, he's saying there's no input to the amplifier circuit, and this final signal emanates from the noise present at the input of the amplifier due to free electrons present in the resistors connected to the amplifier, which move randomly at ambient temperature. So that's like the main explanation of where the signal begins from. It's from the noise that's amplified and amplified over and over again until you get a sinusoidal at the output. Okay, and then why it's a sinusoidal curve at the output and not just any form of, any shape of curve. It says, where is it? Okay, hapa juu, the output would be expected to be infinite. That's if KAV is equals to 1. But the output of any real circuit can never be infinite because the maximum output voltage would be equal to the supply voltage. So the performance becomes nonlinear, preventing possibility of an infinite gain. So the output voltage would develop whose frequency is not resembling the input signal. Okay. And then, yeah, is a question?
Yeah, when you're saying something about where the maximum output voltage is, where you're explaining the whole thing about it being infinite, why it can't be infinite.
Okay, see from the equation, this equation here, the AVF, it's supposed to be equal to AV over 1 minus KAV. But if KAV is equal to 1, then this equation becomes infinite. But that's not possible. So, okay, normally a NI would have a linear output, an amplifier. But the amplifier, because it can't give an infinite gain, it'll have to become nonlinear. So whatever is inputted isn't reflected at the output. It outputs something different. So I hope that explains.
So when something different is reflected on the output,
yeah,
and it's nonlinear, so is that then what happens?
Okay, normally from the calculations, I've seen that because of the output, okay, let me just get a circuit here. Because of the feedback network, that's this part, at least in this circuit, it's one that has the L, C, and L. It's going to get a K that will be different for each frequency. So the frequencies the noise will come in with many frequencies, with Fouriers, whatever, transfer and all that stuff. And then it will be amplified, but only a certain frequency will give back the conditions for KAV greater than or equal to 1. So that's why only some frequencies will be, it will get the KAV being real and positive. The other frequencies won't get real and positive. So that one frequency is the one that will be amplified over and over repeatedly until it comes out at the output. Yeah. So is that okay?
Okay. Thanks.
Sorry?
Thank you. Thank you.
Welcome. Okay, the next question here was about the sinusoidal oscillator over here. So this one has two inductors, so it's the Hartley oscillator. Saying the input, there is no input signal at the circuit. Explain briefly the origin of the starting voltage. So that's what I explained. And then prove that the circuit oscillates at a frequency given by that, and hence show that the oscillation occurs if GMRD is greater than or equal to 1. Okay, so that's what I have here, the Hartley oscillator. This is just drawn differently, but it's more or less the same thing. Okay, and then I've written a note down there about the magnitudes of the capacitors. So, you know, kawaida, when you're drawing an AC equivalent circuit, the capacitors, all of them would become short circuits. But that's not the case for the oscillators, because, okay, it's because of the values of the capacitances. So the CS and CC, which are the ones that become shorts, are usually in the order of microfarads. So they appear as short circuits in the operating frequency, but the capacitances that are in the feedback network, that's C, is in the order of nanofarads. So it will have an extremely high reactance at the operating frequency, so it won't be a short circuit. Okay, so the equivalent circuit of the circuit drawn. So I've drawn there for JFET why exactly it looks like this. So this circuit is a JFET amplifier. So that's the what do you call it? The AC equivalent. So from the circuit, you can see that the V out is equal to negative GM VGS times Z, because negative GM VGS is what will flow through the whole of the resistance marked Z there. But then we also know that the input is what will be found at the G, so it's equal to VGS. So we can get the AV as V out over V in. We get that. And then from here, we can also see what the feedback voltage will be. So it's the drop that will occur at L. So it's ZL over ZL plus ZC times V out. So you can replace ZL with the J reactance for all of them and get K, which will be the feedback voltage of output voltage, which is equal to that. Then you can multiply the two to get KAV. And then calculating Z from here, from the circuit, it's RD parallel with L and parallel with the series combination of C and L, which is what is here. So first I decided to calculate the parallel of the L and series LC, the two on the right of the equation. So I got that equation. And then over here, you also need to be careful about the J's, because when the J's multiply, you're going to get a minus. So you can see that that equation has RD parallel with a negative something. That's because of the two J's multiplying. And then you parallel it with the RD again. And yeah, continue the equation here. And then now after getting Z, you can replace into the KAV equation. That's this one here. And this is what you get. So from the final equation, you can see it has one J, what do you call it, element. and it's in the denominator. It doesn't matter if it's in the denominator or the numerator, but that J, whatever it has, must disappear. So, because we need the KAV to be positive and real, so the imaginary has to be 0. So to make it disappear, we need to equate the parts that the 2XL and XC. So that's what I've written there, and you can get the operating frequency. So that's at omega squared. It's omega naught squared is equals to 1 over 2 LC, and omega is supposed to be equal to 2 pi f. So I've gotten the f naught equivalent. So that will be in hertz. And then at the end, after you've gotten that x2xl is supposed to be equal to xc, you can replace it into this equation, that's KAV equation. So that will be you getting KAV at the resonant frequency. So you calculate that, and it'll end up with KAV at resonant frequency is equal to GM RD. So using the Backusian criterion, you get for your oscillator, you need GMRD to be greater than or equal to 1. And then there's a note I've written here about the what do you call this? The feedback network. So you can see how it has the L, C, and L, and the two L's are grounded on one side. So if you take just that part of the circuit with the V out and V feedback, you can redraw it like this. And you can take note of the loop, that loop I have written. So if you consider the loop current I, the impedance that the current faces is Z loop is equals to ZL plus ZL plus ZC. So if you look at that, it'll end up giving you the same condition that you had calculated above here. Where is it? It's this one. 2XL is equals to XC. It gives you the same equation. So this will help explain why the what do you call it? The crystal oscillator, why the equations look the way they look. So that's the answer for the part B and part C, I think. Yeah, so any questions? Tilda? So no questions. Can you guys still hear me?
No, yeah, we can hear. Please, that part 3 again.
Part 3.
Yeah.
Which one?
That one.
Yeah.
And show that oscillation occurs. So just showing that. Wait, how have we shown that oscillation occurs?
So it's over here. Once you've gotten the resonant frequency, there's the condition that you use to get the resonant frequency. That's 2XL is equals to XC. So you can see it there. So with that, you can replace it into the KAV equation that you had. So you replace it into that, and you'll get the KAV at resonant frequency. Mm-hmm. And then because it's an oscillator, it has to obey the Backusian criterion, which is KAV must be greater than or equal to 1. So that's how it's been proved.
That's okay.
Okay, any other question? Okay, so the next question I had was this one. So the first part says, the diagram shows a Hartley sinusoidal oscillator. The full biasing circuit is not shown. So prove that the circuit oscillates at the frequency given by that. That's the same as what we had before. And hence show the oscillation occurs if GMRD is greater than 1. So that's the same thing we had before. This other part has, can't read. In practice, a piezoelectric crystal is used in a Colpitts oscillator. Sketch the circuit of a Colpitts oscillator circuit. Okay, so you remember the way the Hartley looks? The only difference will be that wherever you have L, you replace it with a C, and the C will be replaced with an L. So the Colpitts will end up looking like this. This is again drawn differently. Okay, and then I decided to do the same calculation, but it ends up as almost exactly the same as for the Hartley. So you need to calculate Z. That's the one shown there in the AC equivalent. And with Z, you can put it into AV, which is the same as before. K here will be different because it will be now the drop through this capacitor in that series LC part. So it becomes negative XC over XL minus XC. So with that, it's more or less the same thing. You get your KAV here, and then you take the imaginary part to 0. You get XL is equals to 2XC. And then you use that to get your operating frequency. And then after replacing XL is equals to 2XE in the KAV equation, you get your KAV, exactly the same as Hartley's. And then your NA becomes the GM. RD is greater than or equal to 1, just like before. Then here I've made the same note about the loop part, which now will have one inductor and 2 capacitors. So your loop, Z loop becomes that. And to send the imaginary to 0 again, it's the same situation as before. XL is equals to 2XE. XC, that's up here. XL is equals to 2XE. And so that, now I can use it to show why the Colpitts crystal oscillator is the way it is. So it looks, this is the Colpitts crystal oscillator. That's the circuit they're asking for up here. Is it? Draw the circuit of a Colpitts crystal oscillator and obtain an expression for the approximate frequency of oscillation for the circuit above. Yeah, it's this one, the Colpitts crystal oscillator. The only difference is from the Colpitts one, you just replace that inductor L at the bottom in this circuit with the crystal. It's the one marked XT here. So yeah, that's it. And then we can look at the AC equivalent, and then the equivalent of a piezoelectric crystal that will have an inductance, capacitance, and resistance. And then in parallel with that will be CM, which is like, okay, when creating the piezoelectric crystal, it has to have like 2 plates to hold the crystal, and that crystal will have a mounting capacitance because it's 2 plates with the electric in between. So that's where the CM is coming from. But then the CS, LS, and RS are like intrinsic to the material. Then here I've written the order of values for each of these 4 NAs. So we have RS, it will be hundreds of ohms. LS, a few Henry. The CS is picofarads and CM is 100 of picofarads. So you can see the CS is a lot less than CM. So if you look at the feedback circuits from here, like we were looking at them before, for the Hartley and Colpitts, it'll look like this. So you'll have the C1 and C2 in parallel with the XT. And then you can replace the XT with the equivalent for the piezoelectric crystal, couple. Then you can put the CM, C1 and C2 together to form the one I've marked here as CP, which will be CM in parallel with the series C1 and C2. And for capacitances, that's how it's calculated. So after that, now you can look at the loop current. And then here, it's because of the total, the total capacitance in the loop is the series of CS and CP, which is here. But then from before, looking at the order of values, you'll see that CS is a lot less than CM. So CS will be a lot less than CP as well. So you can say that CT will be roughly equal to CS, because it's the parallel. Okay, it's the series. Okay, for capacitors, yeah, let's explain that part. Okay, so you'll find that now the frequency of the resonant frequency, that's why it's equal to the Fs from this circuit. Okay, any questions about that? So no questions. Okay. Okay, so the next question. Derive the equivalent circuit for a piezoelectric circuit. Hence, for this crystal, obtain expression for the two resonant frequencies, obtain the expression for the approximate impedance, and using expression in 2 above, plot the impedance versus frequency. Okay, so this is more or less ECT stuff, because once you have this equivalent circuit, it's obtaining the ECT calculation, and then to obtain frequency, this one, yeah. So for the series resonant frequency, it's for the series part. You're just going to consider the LS and CS, because CM will be hundreds of picofarads. It won't be considered here. Its reactance will be too low. So with LS and CS, this is what you get for the series resonant frequency. For the parallel resonant frequency, you look at the loop. So the loop going around. So you consider, you leave out the ends that connect outward and look at as a series CS, CM, RS, LS. So with that, you use it to get CP, which will be the series of CS and CM, which is that. And then the parallel frequency, think about my Fs instead of Fp, should be Fp here. So Fp is equals to 1 over 2 pi Ls root Ls Cp. So there's a note down there. In any crystal, Cs is much larger than Cm, thus Fp is only slightly greater than Fs. And then for the plot, from the filters work from ECT, you'll see that if you have a capacitor in parallel with a series LC, this is the curve that you get. So it will have a capacitive half plane at the bottom. Then upper G, I don't think if you can read it, but it's inductive half plane. And then it will have that last part. So your FP and FS will be at the bottom right here, where you have the asymptote cutting the x-axis and where the line cuts the x-axis. Yeah, I think that's it. Then next part of the question. So the figure shows an oscillator based on a piezoelectric circuit crystal. Draw the AC equivalent circuit of the oscillator. And then utilizing the equivalent circuit of the piezoelectric crystal in A above, and obtain an expression for the approximate frequency of oscillation for the circuit. So this circuit is the same as the one I drawn before. So this one. Okay, the only difference is that this has the JFET. Then here I drew it with a VJT, but it's more or less the same thing. So the equivalent okay, but it'll have more or less the same thing, but then here it'll have the, instead of the BJT here, it'll have the G, D, and S parts with the GM VGS thing here, this one. It'll have that GDS part instead of the VJT. And then you replace XT with this, and that's it. And then what was the other part of the question? Obtain an expression for the approximate frequency of oscillation for the circuit. So that again was this part, that you obtained the F naught is equals to 1 over 2 pi root LC LS CS. Yeah. And then the next question, it's more or less the same thing. At least part A is the same. And then part B, the figure shows an oscillator based on piezoelectric circuit using the equivalent in A above. Obtain the expression for the, yeah, it's the same thing. The same circuit. So any questions about the crystal oscillators? Can you guys still hear me?
Yes.
Okay, so no questions. Yeah, tuendelee. Okay, and then there was this question from class. It's similar to there was in our labs, we had something to do with the phase shift oscillator. It was a BJT based one. This one is a JFET one. So this is the circuit. It'll have 3 capacitors, 3 resistors in the feedback circuit. So I'm sure about this capacitance. Hold on, Cassie. Okay, yeah, this capacitance isn't CC. The capacitance next to RD, it's not CC, it's C. So in the AC equivalent, bado itakuwa hapo. It doesn't disappear. So yeah, this is the phase shift oscillator. This one now calls for vitu za ECTs, loop 1, loop 2, loop 3, and all that stuff. So the AC equivalent is the one here. So because it's the JFET, that's why you have the GSD over there with the current loop. And then one of the conditions for this circuit is that RD must be a lot smaller than R for the calculations to become easier. That's one of the conditions that the circuit will have, such that the current here, you can see I've labeled, the current I through RD is equal to the GM VGS. So all the current will flow through RD, not the rest of the circuit. So with that, okay, from this part, I did the ECT equivalent for the what is this? Current source equivalent, the voltage source equivalent from a current source. So the GM VGS and RD become this. Then I've noted why the polarity of the knee is pointing positive, is towards the ground, because of how the current through RD is, it's going up. So you can see the positive and the minus where they are. So there's that. And then something else to note was the I through the RD was assumed. Okay, I mentioned that already, since R is a lot greater than RD. And then I think that's it. Then you can see the labels for I1, I2, I3 with the VF. So the VF is one that's taken back to GS. Then, so you're supposed to apply KVL on the circuit, like for loop 1, loop 2, and loop 3. Yeah. So, okay, for loop 1, there's something else you need to note. In the calculation, you see I1 goes through RD, C, and R. But here, in the calculation, there's no RD in the I1 part. And that's because RD is ignored again, because RD is, again, a lot smaller than R, so it won't appear there. And then also from ACT, there's the I2 is also considered in, well, calculating for loop 1. So that's the minus I2R, and it's minus because the I2 and I1 through R are pointing in different directions. And then you equate all of that to the voltage source. And voltage source here is negative again, because of the direction. It's not the one pushing I1. Like if the voltage source was to push a current, it will push it in the opposite direction that I1 is going in. So that's why it's negative. So with that calculation, you can get I1 in terms of I2 and the voltage input. Yeah. Then you go now to the loop 2 and do the exact same thing, which is loop 2 is here. It has I2 going through R, C, and R. That's here, the middle part. And then the other part will have minus I1 and R, Apojo. And then the other R on the right will also have minus I3. And you equate all that to 0. And then you replace in that equation, I1 from Apojo, you replace it into that equation and get, okay, it's a lot of calculation. I don't think I can go through it now, but you'll get I2 in terms of I3 and the voltage input. You can see all that calculation in Mingi. Okay, and loop 3 again, you do the same thing. And here you'll note that the VF is equals to I3R. So yeah, here. Okay, I don't think I replaced it in the beginning, but yeah, you do all that calculation utapata I3 in terms of VI, and I think it's just that in terms of VI, and then you can replace the I3 with VF over R and get VF in terms of VI. And if you've noticed in this, all these calculations, I was using S, Because, okay, I find that if you multiply for such long equations, using j omega sometimes will confuse you at the point that you have two j's multiplying, there's a negative somewhere, and those two j's are supposed to give another negative. At some point, you're going to end up getting confused. So in Leona, using the s instead of j omega would become easy. And then at the end is when you replace all the s's with the j omega. That's what I've done down here. And then I also let 1 over omega cr equals to alpha. So it's a lot of calculation. But this part, after you've replaced the 1 over SR with negative J alpha, you get here. So I had to split it up again to prevent confusion. So I calculated the denominator alone, and that's the VF in terms of VI. Then from here, you know the equation for KAV is supposed to be K, which is VF over V naught, times AV, which is V naught over I over VI. So KAV becomes VF over VI. So from here, you divide this VF by VI, and you get your KAV. And you need, again, for the KAV, the condition for the oscillator, you'll have to have this being real and positive. So the alpha cubed minus 6 alpha must equal 0. And you remember alpha is the omega, 1 over omega RC. So there, I calculated the alpha naught. The alpha naught becomes root 6. And now that is equals to omega naught CR, 1 over omega naught CR. So you get your omega naught, which is the frequency of oscillation, as that. And again, just like before, the condition you had here, this one, the alpha cubed minus 6 alpha is equals to 0, is what you replace in the KAV equation, this one up here. This KAV equation, you replace that there, so that you can get your KAV at alpha naught. And after you replace it there, so the alpha naught becomes 6, alpha naught squared becomes 6, sorry, and this is the equation you get, which has to be greater than or equal to 1. Again, the second condition for oscillation. So the end becomes your GMRD must be greater than or equal to 29. So any questions about this phase shift oscillator? No questions. Please, what do you say is the same, but the difference is JFET? I think that part I was talking about where is it? About the circuits. Yeah, the circuit that's drawn here and what I had drawn before, Upper June, I had used a BJT, and here he had used a JFET. But the result is more or less the same thing. It's just that the drawing will be different. So any other question? Okay, so I'll continue with the last part, which I was supposed to present, was the wind bridge. It's this one. So I think this is one of the questions he had left for us the time we had an online class. He left for us a question that looks like this. that you can look from the beginning. Give two conditions which are supposed to be met for oscillations to be satisfied in an oscillator. It's discussed about before. Then the figure shows a basic circuit of a Wien bridge sinusoidal oscillator. What is the total phase shift provided by the two-stage amplifier? Okay, so here you can see there's Q1 and Q2, and you can see they've been separated by a capacitor CC. So these two, this is an amplifier, an oscillator with a dual stage amplifier, like the one from the differential amplifier. It has two BJT amplifiers, and each BJT amplifier will always have a phase shift of 180. So the total phase shift here will be 360, because there are two. It's 180 plus 180, 360. So and the next part was given that R1 is equals to R2 is equals to R, and C1 is equals to C2 is equals to C, prove that the circuit oscillates at a frequency given by that, and hence show that the feedback factor K is equals to 1 over 3. Okay, so that's the circuit, the same circuit. Okay, here is the AC equivalent. So that's more or less the first thing you always do for these questions. It's the AC equivalent. So you draw the AC equivalent, you'll have R5 in parallel with R7. That's at the beginning here. The beginning of this, the first BJT, R5 and R7 in parallel, and the first BJT, and then this is R6, I think. Yeah, R6 going to ground because VCC goes to ground. And the other side is shorted to ground because of CE. And then there's the R8 and R9 after CC, which is shorted, which is a short circuit. You'll have R8 and R9, then the BJT, that's here. Then R10 going to ground because R10 is connected to VCC. And then over there you have your output connected. Output will be connected after the CC here at the end. And that is fed back now to the feedback network, which is this whole thing here. So the feedback network will have R4 going to ground because from the connection, it goes around. So this is the connection going back from up here. It goes like this to R4 and then down all the way until this side where you have CE connected to ground. So the R3 won't be showing up in the AC equivalent because R4 will be connected to ground through CE. That's CE on the far side here in the middle. Then the other side will have the C1 and R1. That's these ones here, C1 and R1. And then you'll have your output, your feedback being tapped from there. So that's the feedback. And after that, you'll have C2 and R2 in parallel, then going to ground. And then they have labeled the first BJT amplifier, second BJT amplifier, and the feedback network. This is explaining the 360-degree total phase shift. Okay, and then because now you know that the BJT amplifiers, the two of them will give a total phase shift of 360, and KAV needs to be real. So that means that the feedback network should also be real. Like the amplification, the feedback constant K should be real. So that KAV, where you have A being real and K being real, will be real in the end. So you come here. So AV is equals to V naught over VI. V out over VI is real and positive. So K must also be real and positive to make KAV real and positive. So K is VF over V naught. And VF, I think I marked it here, VF and V naught. So this is a simple connection now. Because once you've gotten from this complicated stuff to here, it's like you've solved everything. So you'll have the VF being tapped in between. So it'll be the drop in the C2 parallel, in the parallel C2 and R2 combination. So it's this one here. So the parallel combination over the total, which will be the C1 and R1 plus the parallel combination. So that's this equation here. So with VF, you get, with that calculation, again, I used S to avoid confusion. And I got here. And now at least it's a little bit easier. You can replace the S with J omega and the 1 over S with negative J over omega. And then from the part that was mentioned above here, the C's are equal and the R's are equal. So after replacing those, after replacing all of that, you get here. So the calculations go on with the multiplication and addition, and then you get K, which is VF over V naught. So the V naught here cancels, and you get 1 over J omega CR plus, all of that. And then you get 1 over 3 plus J something. Now that something in those brackets are what you need to be, at the imaginary part, so you need it to be zeroed out. So you equate the omega CR to 1 over omega CR. That's what I did there. You get the omega naught squared is equals to that. And then you can get the omega naught. And F is supposed to be omega over 2 pi. You divide those two, and you get F naught, which is what was being asked for at the beginning. F naught is equals to 1 over 2 pi RC. And now for the K part, again, you take the part that you had, the condition for that you used to calculate the F naught, and you replace it in there. So that will mean that the J becomes 0, and you'll be left with K is equals to 1 over 3. That's it. Sequence nimeandika. And I think that's it. So any questions? Okay, in the RC oscillator question, I think Cramer's rule can, let me see, show the workout. The RC oscillator, which RC oscillator question? The phase shift. In this question, okay, I'm not sure about Cramer's rule. Your stuff mi sikumbuki vizuri sana, so I think this one gave the workout easy. Okay, not easy, but well enough, so that's one I used. So I'm not sure about Cramer's rule. Okay, any other question? So I think that's the end of my presentation.
All right, thanks, Avo and Celeste. I don't know, was Nigel also supposed to present?
Apana. Celeste has covered everything.
Okay, that's fine.
Nigel. But
Ah.
there are questions you did, yeah?
Only one question. Yenye nimetumwa kwa group.
Okay, sorry. I
Just
took so much time. I didn't
ni sawa.
have time for you, sorry.
It's alright.
That's fine. So thanks, Alvo and Celeste, for having presented today. That was really helpful. So I don't know, do you guys want to like panga for what we'll do on Thursday? I think we're meant to do digital. Yeah, we're meant to do digital on Thursday. So how do you guys want us to like conduct that session? Anyone? Hello.
Hey, Sean.
Hi.
I know you're waiting for people to talk. They're going to talk. I think people are looking at first papers, so people are listening. They're just waiting for you to give direction.
Okay, so I think digital isn't much of a theoretical like unit, like analog. So I think we can just spend the whole session just going through questions. Had we finished the digital content? I don't know. Had we actually finished it?
So I asked Bill. Bill said, I don't know if, yeah, okay, Bill has said that, but he didn't finish. He said we read for ourselves hardware programming.
Okay. So do you guys want we go through the remaining part of hardware programming on Thursday, or do we just focus on questions of the topics we've already covered with Prof. Mwangi? Okay, I'm seeing Celeste is saying we just do questions. Okay, two people are saying we do questions, so I guess we'll just do questions then. So let me check here on Inkwell. Do you guys want we focus on like one paper, or like someone, or like today how Celeste did questions from one topic and then Alvin did questions from another topic? Okay, I'm seeing so that if people have questions already done, please present. Does anyone have questions they've already done? Okay, I don't think anyone has done digital. So I think then we should do like today. So like we prepare like the first topic I saw was logic families. So like someone comes, is done, like two people come, they've done questions on logic families. Maybe another two people have come, having done questions on semiconductor memories. Is that fine?
Yes, that's fine.
Okay, so Sigicho was already nominated to do logic families. Does anyone else want to do that with him?
I will do it in logic families.
Logic. You can do each one of you can like do two, then just come and present it. So next one was semiconductor memories. So who wants to do that? Anyone?
When is the next meeting? On Thursday.
Yeah.
Okay.
So okay, I'm seeing Nigel will do semiconductor memories. Does anyone else want to do that with him? And Alvo, okay. Then the third topic is programmable logic devices. I don't know how far someone could do on that. Okay, so does anyone want to help there? Anyone? There's a lot in PLD that wasn't covered, so it's hard to gauge. That's what I'm also wondering, thinking, because can't ask someone to like go through all of that. I remember like how Bill said that in preparation for exams, we could just leave one topic as like the bad one in which none of us would want to do. Do you want to leave PLDs as that for digital? Then we just focus on the first two. Okay, then no response. Tough crowd. Okay, then I think as of now, yeah. And then I think as of now, we'll just do that then. So on Thursday, we'll have Kishiro and Fiona doing logic families, and then Alvo and Nigel will be doing semiconductor memories. So everyone, thanks for coming. Thank you.
There's a question.
So Daniel is asking if we can meet on Saturday instead of Sunday to do math, because it's too close to the exam date. I have no problem with that personally. Do you want to put it to a vote now, or we do it on Thursday? I think we can do it on Thursday because it's already like 11:15 and it's late. Yeah, we can do it on Thursday. Fine then. So everyone, thanks for coming today. Thank you, Celeste and Alvo, for your presentations, and let's meet on Thursday. Bye.